Now let's look at the problem of minimizing the number of distinct distances among a set of endpoints. For example, in this picture we have two distinct distances, the blue distance and the green distance. We could try using the same idea that we had in the previous problem, where we drew circles from the points. And it almost works. Assume we have t distinct distances, g1 up to gt. From every point we can draw t circles, the first circle with radius g1, the second circle with radius g2, and so on, and the last circle with radius gt. Since this is all the possible distances that happen in this point set, it can be argued that all the other points must be on these circles. So in other words, there should be no point that is outside these t circles. And the same property should hold if we draw the circles centered at some other point in the point set. This means we have a lot of incidences between these circles and the points. In fact, we have 2 times and choose 2 incidences between endpoints and these empty circles that we drew. This is because for every pair of points, we can define 2 incidences. One incidence based on a circle that is centered at the first point, and the second incidence based on a circle that is drawn from a center at the second point. So we have the following problem. We have endpoints and nt circles, and we know that these points and these circles define at least n squared incidences between them. We could try to use the previous technique, however we have a big problem here. And that is, as opposed to the case of unit distances, we could have very high edge multiplicity here. This is because the circles that we drew don't have the same radius anymore, and thus we can have 2 points such that between them we have roughly t different edges. This is a big problem if we want to use the crossing number lemma. The solution to overcome this problem is to consider 2 cases. We again build a graph with n vertices and roughly n squared edges. However, we need to treat the 2 cases of low edge multiplicity and high edge multiplicity differently. Consider edges with low multiplicity. In other words, consider edges where between 2 vertices there are at most k edges. We can have an updated form of a crossing number lemma, which says the number of crossings in a non-simple graph with e edges such that there are at most k edges between every 2 vertex is at least so much, or e cubed divided by k times n squared minus some small factor. I will leave this as an exercise for you to prove, but assuming we know this theorem, we can now proceed as before. Nt circles define n squared t squared crossings, which is a strict upper bound on the number of crossings. And from the crossing lemma, we know that the number of crossings is at least e1 cubed, where e1 is a number of edges with low multiplicity divided by k times n squared. If we write this way, we know we now have a bound on e1. Let's leave this bound as it is for now, and let's consider the edges with high multiplicity. Consider 2 vertices with k edges between them, for example with 3 edges in this picture. Each edge is defined by a circle centered at some point, and it is obvious that the center of such a circle must be on a line that is perpendicular to the line segment that connects the 2 points or the 2 vertices. In other words, 2 points with more than k edges between them define a heavy line with k points on it. In other words, a line is heavy if it passes through more than k points, k input points. And we know that every pair of vertices with more than k edges between them should define a heavy line. How do we bound the number of heavy lines? We can use the Zermelo-Trotto theorem. Assume you have m heavy lines in the point set, and these m heavy lines define a total of I incidences between them, between the heavy lines and the points. We have a strict lower bound on the number of incidences, since every heavy line defines at least k incidences, we know that the number of incidences is at least m times k. However, using the Szekely theorem, we know that we have an upper bound on the number of incidences. Using this, we can conclude that m must be at most n squared divided by k cubed. By plugging m here in the Szekely theorem, we can conclude that the number of incidences between the heavy lines and the points is at most n squared divided by k squared. Let's consider one such incidence. So a point blue from the input lies on a heavy line. The way we constructed the circles, we know that we have drawn T circles centered at this blue point. Such T circles, of course, cross this green line at most 2 times T times. Every crossing can be on an edge, and such an edge could be part of a high multiplicity edge. In other words, there could be k different copies or different edges between the 2 vertices that are at the end point of such an edge. This means that there can be at most the factor t more edges with high multiplicity than the number of incidences. Observe that this is a very pessimistic bound, and in fact it is very difficult to achieve this bound. But we are only looking for an upper bound, so this suffices for now. So now we have an upper bound on a number of edges with high multiplicity. The number of edges with high multiplicity is t times n squared divided by k squared. The number of edges with low multiplicity is also bounded by some expression over here. And we know that these 2 edges will be all the edges. In other words, the number of edges with low multiplicity plus number of edges with high multiplicity should add up to roughly n squared. These 3 facts are the only things we need from now on. So from this 3 facts, we like to derive our bound. Remember that we can choose k to freely as however we want. It turns out the best choice for k is this, some big constant times the square root t. If we choose this value for k, then E2 is bounded, upper bounded by this expression. If c is big enough, it can kill whatever constant lies hidden in the O notation, and we can conclude that the number of edges of E2 is at most n squared over 2, roughly. Since E1 and E2 should add up to n squared, roughly, it follows that E1 should be at least n squared, or some constant times n squared. By plugging the bound over here in the last equation that we have, we can get to this bound, and after further simplification we get here. This might be a bit difficult for you to read, but it basically means that n squared t squared is bigger than some constant times n to the 4 divided by the square root t. And further simplification yields a bound that we're looking for, that the number of distinct distances is at least some constant times n to the 4 over 5.